Merci, bonjour. Alors,
Good morning. Today we're going to be discussing materials durability. We're going to be talking about time, and time is probably one of the most difficult things to handle in materials. So if we take our guiding thread again, we have now reached durability of materials after discussing multifunctional architectured materials from atoms to we talked about modeling, the choice of materials and processes. We showed how materials could be compared in view of specifications. Today we're going to talk about materials durability. We'll discuss modeling again when we talk about the implementation and integrated modeling. Of course, in only 1 hour we can't discuss all of the issues of durability and behaviors of materials, but we're just going to be brushing upon a few aspects. The lecture will discuss both wear and creep as an illustration of typical durability problems, and we're going to be looking at a fast-moving trend, which is the self-healing trend for materials. There will be a seminar by Eric Andrieux from INSAE Toulouse, who's going to tell us about one of the aspects, which are issues of corrosion. And for this afternoon's working group, I decided that we should focus around corrosion, mechanical corrosion. We'll have a certain number of presentations about these issues. So we won't cover all of the problems of materials durability, but just try to illustrate with one given case, which is the case of corrosion, interaction with the environment, how what the questions are that arise from that. So this diagram is something I showed you already when we discussed problems with design, and I said that what was well developed were methods where you design for heaven, basically for things that last forever. But that doesn't really happen, because there's a certain number of degradations that are going to occur as the component is used. So it can be degradation caused by the fact that you have a deferred variations caused is what results by creep, where there only been elasticity deformation at a given time. You have fatigue, which is a kind of a treacherous way, because it looks like nothing is happening, but there's more or less of that nothing, and then eventually it breaks. If you look at the clip on your pen, you take it on in and out of your pocket, and then after a while the clip on your pen drops. That's typical. And then there's corrosion, and then there's wear, which is basically behavior of materials in time in situations of contact. So in terms of design, there are two ways of envisaging the problem. One is to say, I'm going to place myself in a situation where this is not going to happen. For instance, operating temperatures which are well below half of its melting point, well below the fatigue limit. Of course, I can try and design things like that, but then that means you have over-dimensioned components, not necessarily a good solution. Another solution is to say, I know it's going to become damaged. I'll just try to make sure that it doesn't deteriorate faster than the lifespan of the given element I'm trying to make sure, for instance, you have the number of cycles an engine must run, make sure that it is more resistant than that. And then there's another solution, which often appears. Sometimes you're going to say, I'm going to have damage over time, I need to find a system solution to prevent that. Thermal treatment, surface treatment, protective treatments. Typically what you're doing when you're hardening a surface to make it more wear resistant, or more fatigue resistant. So that's the overview. What we're going to be discussing today are a few of the key issues in materials durability, and one of these key issues that comes back over and over again is the fact that usually you want to do accelerated testing to say, can I reasonably evaluate the lifespan of the component? There's a well-known story, I think it was at IDF. He was asked, when's the best time to change a post? And he said, well, it must be just before it falls down. But that would mean very long testing, wouldn't it? So how can you have accelerated testing? Usually what you do is that you increase the conditions of solicitation, increase temperature, increase the constraint, increase the variation rates when we talk about materials, but essentially, if you change the conditions of solicitation, you're just accelerating the phenomenon or actually changing the physics of the phenomenon. That's something that you can find for the durability of nuclear power stations, but also waste storage or engine durability or turbine blades and so on and so forth. How can you accelerate the testing? Second aspect that's critical is to have a look at the systemic issues that involve both altogether materials, environment, and geometry. That occurs a lot in corrosion and wear. And the third point is how can you try to deal through remediation. I told you about surface treatments, but I'll also try and tell you about self-healing systems, which in a sense are going to give us a bit of a glimpse of the last lecture, which will be about bio-inspired material. How can you heal the damage as it is occurring, as it were? So I'm going to start by telling you about creep, how one can reasonably expect to have accelerated creep testing. Then the question of wear. I'm going to try, it's actually quite an old approach, but I think is very valuable and has not been sufficiently exploited. In the sense, what I was saying in the first lectures is that these problems are so major that we often tend to confuse qualifications of materials and understanding of the phenomenon. I think we need to understand the phenomena with materials that can allow us to understand. The case of corrosion, discussed by Eric Andrieux, and this afternoon's workshop, we will hear more about hold over time in the lecture about extreme conditions. Of course, the seminar will be dedicated to the aging of materials under the effects of radiation, where there again time is of the essence. So, creep, wear, and self-healing solutions. Creep is actually quite interesting because this is an approach that was developed, let's say, over the past 20 years or so, that has been used across several systems, a lot of improvements in the principle, but which is based on an understanding, a physical understanding of plasticity phenomena. The cases that I'm going to be studying are those where the plasticity of the alloys is based on dislocation. The very simple question you can ask is, what if I'm testing traction, pulling, what is that going to tell me about aging and creep, which is long term? So how long, for instance, can I operate a thermal exchange array in a nuclear power station? The basic idea was to say, essentially, we're trying to extrapolate over time, and in order to do that, you need to have reliability of the mechanisms. If you change the type of solicitation, you can change the deformation mechanisms, and the result of that is that you can be completely off the mark when extrapolating. So this appeared in the 70s, so quite a while ago, what were called Ashby creep maps, Ashby again, to say there's a constraint on a material, but it's the constraint versus a rigidity, a hardness at a given temperature. And what's relevant here is what is the importance of thermally activated phenomena compared to the melting point, which is also a measure of the system's cohesion. So when you map deformation here, here we're talking about power of 10, temperature, and then a normalized shear stress. And the idea is that if you have very low stress or a very high temperature, a very low constraint is not sufficient to make the dislocations move, but it's sufficient to make the punctual faults. And it's actually, you can actually get a migration of the faults. It's a linear. It's what is called diffusion creep laws. So if you have very high temperature, these faults can move, and if you have lower temperatures, they essentially behave differently. So there are two different laws based on stress and on grain size. If you increase the constraint, of course, you still have these faults that are going to be moving around, but also the dislocations. And then if you have very high stress, they actually slide, start to slip. If your constraint is low, but it can't slip, but it can move by relying on these faults, you have another type of creep that follows another type of laws. Here, typically, power versus constraint is much higher than for diffusion creep. So, if you have an accelerated regime for dislocation creep based on the constraint with a high power, if you, based on that, try to understand what's going to happen with a lower constraint, the result will be wrong. So these models open access to stationary creep phenomena. You have a given constraint, a given deformation that is time dependent. Initially, there's going to be a transitionary state, and then an accelerated speed. And then, in the 80s, under the influence of Cox and others, here it's for highly pure aluminium. The question was, what is the difference between a creep test and a pulling test with an imposed deformation speed performed in a system where creep is controlled by dislocation movement? So here the idea was to say that a dislocation is silly and it doesn't know whether it's working under imposed pulling or a creep. So if you test, if you impose a stress with a given speed, a given constraint, in your creep test, you may be able to predict what's going to happen when you apply a constraint and that you're measuring a deformation speed. So you have a few tests here that were carried out at different temperatures with different degrees of stress, of strain. The creep tests are the full ones, and the other ones are the hollow ones, and essentially they are actually quite well aligned. So at least in these scales of temperatures, there's no real reason to believe that you have different types of deformation. And it's not always the case, but it was here. So if you continue the parallel here, and if you say that dislocations are stupid beings, if you have a stationary, a constant creep condition, it's essentially stable, and deformation is essentially, speed of deformation is essentially stable too. You have the deformation speed based on deformation, you have a transitory period here, you have secondary creep, which is stationary, and then the material is going to become damaged. Of course, damaged means different things, but basically, for a given constraint, deformation accelerates. If you look at a stationary creep, minimal creep is a stationary structure dislocation state. But if you look at the behavior in terms of speed of imposed stress, the state of saturation in this type of test which you can obtain with very high deformation, and the equivalent in terms of imposed stress, speed in the stationary state in creep. So it was quite simple here. You have a dislocation that's essentially constant because of the balance between the stress you're creating and what you're annihilating. When you have more and more, they tend to annihilate each other more easily in pairs of dislocations, plus B minus B, and you have a dynamic balance with a defined speed that should describe the stationary condition, which is dynamic with imposed constraints. So, with a tensile test, how can that translate into creep test? Can we actually incorporate microstructure evolutions into this? I will show you that it can be applied to much more complex instances. But another question is, how can you take into account the fact that a dislocation is not necessarily the constraint you've applied? It can be a constraint that's modified. How can that be taken into account? Let me start by showing you internal variable models, and I think they're actually excellent value for money. They're simple but allow you to explain lots of things. We'll then see variations on this model, incorporating microstructure. We're going to see how incompatibility constraints can be built in, how we can try to describe certain types of ODS materials, some that are actually ill-adapted, unfortunately, the ones that we really would like to be using, and then we'll reach today's conclusions. So, the skeletal model, the most elemental model in terms of the approach of variable internal plasticity, is that you have one variable. It's the dislocation density. So, of course, you can fine-tune the model. You can have fixed, mobile, dislocation in the different planes. You can make things much more complex if you want to. But what can you do with the simplest version? Second point, the dislocation motion to overcome obstacles contribute dominantly to plastic train, where direct diffusional flow is dominated by the deformation by dislocation. Other obstacles can be either other dislocations or fixed obstacles, such as grain boundaries, precipitates, and they control the mean free path of dislocations and the dislocation storage kinetics. They're going to be terms of annihilations. They can be annihilated in pairs, and then they're going to be terms of storage, which are essentially going to be the obstacles encountered where they can't move further. And then the dynamic recovery processes control the dislocation annihilation kinetics. So the basic model here, which you can work on indefinitely, is the Cox-Mecking model, which is also very simple in principle. There's a relationship between speed of deformation and constraint, but the idea is that it should be considered not as such, but in relation to the intrinsic resistance of the material you're examining. And this intrinsic resistance is that of the crystalline network, but as you are deforming the material, you're accumulating dislocations, which increases the material's resistance. So the Cox-Mecking model is designed to normalize the constraints you're applying based on the resistance of the material, which itself is connected in a pure metal to the density dislocation within that material, which is the meaning of this first equation, the constraint normalized by the reference constraint, sigma with a circumflex, it must be equal to the speed of deformation normalized by the reference speed of deformation. And the idea is that the reference constraint is square root of the dislocation density. So you're actually overcoming the obstacles, which it's essentially dislocation. You could feel that you could add lots, precipitates, grain boundaries, and so on. So the way that you're going to note this, you have a term here which is a term of annihilation and a term of storage here. You have the three average free path, and it's proportional to the dislocation density. Because you're describing an evolution in time. So if you write this equation with time in it, here you would have rho to the squared. It would be by pairs. Two opposite dislocations fall on one another and annihilate each other, and then dynamically restores with a growth that is proportional to the speed of its movement. So what remains is, what is the mean free path that's here? When I only have dislocations can be connected to this amount here, average distance between dislocations. If you add precipitates or grain boundaries, you're going to have mean free path that's going to be modified by these new obstacles. So this can actually be sort of integrated easily, and a miracle, you end up with a Vos law, which was developed long before these approaches were developed. It's a classic description of mechanics for plasticity with saturation. And what you have here is, in fact, I don't know why it sort of turned into bright purple, but you have this Vos equation here. And the difference between that and a purely phenomenological interpretation is you have a direct interpretation of various parameters. So the law of Vos, constraint at saturation is going to be connected to the storage rate and annihilation rate, and the θ2 law that you have in this deformation here is essentially how the deformations are going to be stored initially in stage 2 of the deformation. So you can very well integrate the equation in the same manner, not with a constant speed, but with a constant constraint. What you obtain is a Vos equation for creep, rather than for imposed deformation, speed deformation. What you can do is test. You can have tensile tests at different speeds. You can have jumps. You can have tensile tests carried out at different temperatures, and based on that, you can extract the parameters allowing you to adjust your Vos traction law and use these parameters to predict creep. So obviously you don't have the first part of creep. It won't give you the tertiary creep because other mechanisms become involved at that point. So if you want to have variations of these models by including, for instance, microstructures, what you can do is to inject grain size. Incorporate grain size that's going to appear in the mean free path. When the grain size is above 20 microns, that can very much have an influence on the mean free path. When they're smaller, you're going to feel the dislocations in the grain more in terms of dislocations accumulating, and there are going to be other terms here. It's going to be terms of internal constraints because of grain-to-grain incompatibility. Usually when you reduce the size of the grain, the more you do that, the more you're going to lead to look closely at dislocation. Then if you want to include a precipitate, the most natural way to do that would be to include it as an additional threshold. Say the dislocation must cross the precipitation constraint plus the obstacles linked to dislocation. So depending on how strong the obstacles are, it'll be either a direct average or a quadratic average. You can fine-tune that too, and you can also have precipitates that serve storage for the dislocations. You can have dislocations that can store around precipitates. That can actually be quite subtle. Because they're stored around the precipitates, they can or not remain where they're being stored. What I'm showing is a large ramification of models, allowing you to take more and more phenomena of microstructure into account. The benefits of these types of approaches is that creep tests are much longer than tensile tests. So you use tensile tests to try to predict creep. Microstructural evolution, such as precipitation, may themselves depend on time. And you can very well imagine that while you're carrying out your creep test, as it's going to be much longer, the precipitation state in the material may actually change in the course of the test. And then, of course, recrystallization may occur when you've got a deformed material. And as I was saying last time, you may also need to include possible changes in texture, dislocation density, with phenomena that are indexed on time rather than speed of deformation. So one way of including these variations, in some cases it's well adapted, in others not so much, it's to evaluate separately the time evolution of microstructural features. That's the sort of thing that can happen in an instant where you have a precipitation which over time is coalescing. I'm not creating a new phase, I merely have the same precipitates with the same volume fraction, but they are increasing. You're changing the distance between the precipitates and therefore the mean free path, and you're also changing the storage capacity of the precipitates, and therefore the changes of microstructure happen much slower than dislocation. So you can reasonably separate the two approaches to have both an evolution equation for the microstructural parameter and an equation for changes in dislocation densities for a common value. So again, here you can feel that this is probably going to work as long as the microstructural change is not too dependent on the constraint. So in fact, the bigger your precipitates, the larger the chances it's going to work. So you can gradually include the physics that you need in order to see how you can change the microstructure while also changing dislocation densities. So this is one example carried out on an alloy of aging effects. You have deformation speed. The test was carried out with an imposed deformation speed based on that to identify the parameters. You have little black dots here, which are the predicted behavior, creep behavior, based on what was identified in tensile testing. So the hypothesis is that the mechanism remains essentially the same. And then you carry out the same test with a material that is not aged. A material where you have a situation where you can actually precipitate and then coalesce the precipitation state. This is what is done here. You have the experimental points here, little crosses, and you have the forecast behavior with experimental points that takes the evolution in the microstructure into account. If you have precipitation kinetics here and then coalescence kinetics. So typically this is what you can do in some instances where you can reasonably disconnect microstructural evolution. It's not always the case, but in some cases it is. So if you now want to discuss polycrystalline materials with variable textures, you need to get back to basics. you think you're imposing a constraint, but it actually can't see that constraint. It sees the constraint linked to the fact that the grain in which it is influenced by other grains that are not deformed in the same way, or that the material in which you are contains inclusions which have not become deformed, while the rest of the material has. So you have a constraint which is polarized. One way of taking that into account is to say the dislocation cannot feel the constraint that's being applied. It can feel that minus an internal constraint that's preventing it from moving. And obviously it's that you're going to have to compare with a reference constraint, which is the obstacle constraint. So I'm going to show you how you can try to do that. This is model 0, the Cox-Making-Estrin model. The 0.5 model is to see dislocation does not see that constraint. It sees the constraint minus the internal constraint, and the obstacle it needs to cross is not just a dislocation. There's also network friction. So what you're going to see when you see that, this is what was done on zircon alloys, is that the internal constraint is not just an incompatibility constraint. You're actually building incompatibility, but it is itself relaxing, slackening, with kinetics that are not necessarily the same as those that are connected to deformation speed or the movement of dislocations. So what you have here is a formulation of this internal constraint relaxation. Here you need to go into real mechanics of polycrystalline materials, and then you relax those proportionally to the amount of stress already here, and you relax it either independently of the deformation speed or dependent on that speed. So you can have diffusional relaxation or through rearrangement of dislocation within the grains. That is the type of prediction you can have for deformation speeds based on creep deformation with simple tensile tests. I'll just finish this section by discussing how you can examine situations where there is dispersion within the material, dispersion of phases that cannot be penetrated by that, because there are storage signs. So here we have two alloys with oxide dispersion that have been studied, the work carried out by Eurostream's team, to have either homogeneous or heterogeneous distribution of the precipitates. Here you have these creep tests carried out based on constraint, deformation, and you can see here 551 megapascals here. You can actually fall dramatically in creep speed. If you have here, so it's exactly the same procedure as what I showed you earlier. You have traction tests with speed jumps, temperature jumps. You describe all of that with a Vos model modified by the fact that you're storing it in the precipitates and that your precipitates are also obstacles, and based on that you can deduct the deformation speed. Just one thing before we end that description. How do you take into account the fact that the particles are or are not dispersed homogeneously, depending on the design process? In fact, the two ways of doing that is to have Voronoi meshes and to see what is the local fraction of particles, and having an approach, a deformation, a polyphase material deformation approach, where you say each grain has a local volumic fraction. Well, so now, to finish with this section, I'm not saying that it's always possible to have tensile tests to determine creep, but in fact very few ingredients. It's possible to have a description that can gradually include materials physics. Let me give you a second example of durability. It's the example of wear. I'm not going to go down into as much detail, but just show you an overview of how you can understand wear in materials. Again, based on the question of the local mechanisms involved. And here, I think these approaches would actually deserve a greater experimentation on more simple materials than what is usually used. What is wear? Wear is the process of removal of matter by friction between two solids. So you can see that these are situations that are pretty annoying because you have two materials. You have a geometry, it won't be the same, rubbing a pin or a pawn or a cylinder. And then if you have a lubricant, hooray! If things is happening in an atmosphere that's a bit slightly chemically aggressive, you're sure that you won't understand a thing. But you can always try to see how you can actually envisage the problem to try and gain some understanding. There are several processes at work in wear, in the same way as a certain number of processes active in creep. The difference is that in creep, you have few active processes. So you can have creep maps that are bottom up. You can describe reliable models and then, based on these, try to build creep maps. With wear, things are much more annoying because you can only rationalize empirical maps. You have a certain number of mechanisms. You have adhesion, abrasion, you can have wear by oxidation, you can have delamination, you can have melting. It depends on the speed at which you're rubbing, the force at which you're pressing, the temperature. All this is happening. So the experimental parameters that you have are a load, area in contact, sliding velocity, mass loss. The materials parameters, of course, is hardness, pretty simple. You're not going to look at sophisticated stuff such as elasticity limits and stuff like that. You just want to know whether it's hard or not. Then you're going to have thermal diffusivity. You're creating heat through rubbing, which is going to diffuse across the material. It's not the ambient temperature, it's the temperature where the rubbing is happening. And that leads you to create dimensionless parameters, force characterized by F and AH, speed, characteristic speed connected to a size of the contact, and diffusivity. So the empirical data maps, you have them here. There's a whole lot of data that was brought together by Mike Ashby on low carbon steels. And to the right you have something that can actually help you to rationalize that with the dominant modes of wear. And if you want to have something that is going to let you discover what is going to happen over time, you must stay within the constraints of solicitation of stress. So how are these maps derived? I'll just give you the basics. The first thing is that you really need to characterize the temperature of sliding surfaces and to distinguish between the overall temperature and the flash temperature on the asperities of the surfaces. You're going to see the various types of wears, either because you have a welding between asperities, because you have melting, seizure, oxidation wear, or just because you're just tearing off matter. You've reached maximum ductility and therefore you're removing materials. And then what you're going to do is to draw a map of these dominant mechanisms. So a few simple hypotheses. The reason I'm giving you this example is that it looks really incredibly complex, but in fact you can describe it with a few simple points. In fact, most work coming from friction is turned into heat. First thing you need to know. Second thing, heat generated at the contact between the two materials diffuses in the material. Third point is that there's a difference between the average bulk temperature and the local flash temperature, between two asperities that are being sheared. And we're going to try to calculate these. So what you need to bear in mind is very simple. When you have two metal materials that are in contact, there are going to be asperities that are going to be touching. So of course it's the points that touch, so you have huge constraints. And then of course they flatten, and you end up with contact points that are larger. If you have larger contact, you have smaller constraint until the contact reaches such a large size until you reach the material's elasticity limit. This is all very, of course, basically, but Bowden and Tabor had suggested this in the 50s to explain a phenomenon that had been noted by Leonardo da Vinci quite a while before that, is that when you put a metal on top of a metal, the force required to move it does not depend on the surface in contact. So it's counterintuitive. And that's essentially due to the fact that the contact surfaces are the same surfaces that you're going to need to shear. So this was evidenced by Bowden and Tabor in the 50s and had actually already been tested by Maxwell. He wrote Maxwell's equations, and he thought it was okay to look at these friction forces, and he'd merely measured the electrical conductivity of two metal solids in contact. So the idea here is to take a geometry of a pawn on a disc and try to calculate the temperature generated at that particular place. So the ingredients are, of course, friction coefficient, force, speed, dissipated power divided by the nominal contact area. It's going to be an input flow, which is going to, at least part of it, is going to be diffused into contact, the other into the disc, and the respective fractions, of course. There you need finished elements to try and figure out how they separate. The characteristic length is also something that you're going to need to calculate. And then you have the diffusion flow and determine that it's going to be the difference in temperature between the contact temperature and the nominal temperature divided by the characteristic length multiplied by a thermal diffusivity quotient. So you can see what the temperature of contact will be based on the material temperature and a whole bunch of stuff depending on the normalized speed, among other things. So once you've obtained that, the next step is to look at how you can have a pawn to disc contact to asperity contact. So you need an additional input here, which is the number of contacts. What mechanics can give you directly is the total contact surface, but you can have either a lot of little contacts or a few large ones, and you need to add that, to factor that in, and that gives you the flash temperature. Based on that, the type of equation you're going to obtain to resolve this model, I won't go into the finer details, but basically the physics I've just described, to which you add the algebra, and then you can deduce the flash temperatures, which is the important point, at the asperity, based on normalized speed and normalized pressure. Once you've done that, you haven't really calculated the rate of wear. You need to couple that with a mechanism that results in wear. It can be, I'm creating a little bit of oxide which is being removed, and therefore I need to know how the speed at which the oxidation layer is going to thicken. Or I locally melt the material, and by melting it locally, the melting means that some of the material is going to be removed. And there what you need to do is to balance out the latent fusion temperature with the flow of heat that you're creating. So these are the various mechanisms involved, and based on these different mechanisms you can obtain a dominant map, not only in terms of wear, but also a wear dominance map with equivalent lines of speeds of wear. So I think I'll just finish now, because I can see that time flies, with the final point I wanted to discuss for this particular lecture, which is truly in the making. These are issues which I think have become indecisive, not practically, because there are a lot of interesting studies, sophisticated studies that have been carried out with industrial materials, but it's being done less and less on materials that would be models. And I think it's a big problem in durability, the fact that you should be able to take your time to study time, as it were, to have model materials to allow you to understand oxidation, corrosion, wear, creep, and to have an approach that could bring you back to the basic mechanisms. But here, this is another extreme case. This is something that's really in the making. It's the field of self-healing materials. I'm going to give you one example of a self-healing material. It's bone. Particularly spectacular. You know, you have the outer bone, which is the cortical bone. That's a vertebra. The other one, a 27-year-old's vertebra, and the other one is a 97-year-old man's vertebra. I chose that because you always tend to think that osteoporosis is a disease that only hits women, but men get it too, but they get it later. But usually they do get shorter and then snap after a while. So you have the outer part, the cortical bone, which is dense, and the internal part, which is a foam, the trabecular bone. I was telling you that foam was very interesting. This is a good type of foam in there. You can see that on the right, things are not going to be running very smoothly. There's almost nothing there, so it's going to go crunch. That's what happens when, people become old and bent. It's what happens, and then a certain number of bones break and all that. So why are things working well on the left and not on the right? You can see that there are characteristic directions here. What's interesting is that when a baby's born, it's just been swimming around in placenta, is unaware of gravity, and there's no particular direction in the bone. It's only in the first weeks where he starts to feel that gravity exists, that actually the bone structures start to find an orientation. What's interesting is that bone places matter exactly where it's required. It's essentially mineral. It's a mix of mineral and organic, this white substance here. But it actually deposits itself in the directions of maximum contact. If you look at a femur, you can really see the lines of maximum density. Everything's perfectly well lined, which is why the bone is called an organic cathedral. So how do things work? Inside a bone, there are three types of cell. I always get these wrong. So you have the osteoblasts, which place mineral substance. You have the osteoclasts that eat this mineral substance, and you have the osteocytes that tells the other where they need to get to work. And that's actually very, very clever. It's very economical. Minerals are very expensive for living organisms, so it takes mineral matter where it doesn't need it and goes and deposits it where it's needed. So in a sense, the system is self-repairing, self-healing. If something is not going well, you can bring more material, matter there. So what happens when you age is that your osteoclasts are still doing fine, removing material, but the osteoblasts are not doing, and the osteocytes are completely out of it. So the system goes completely haywire, and you cannot create bone where you need it, and that's how the bone hollows out, and you end up old and bent. So obviously that is pretty much the ideal situation. Of course, we'd like to be able to make something that's as good as bone, that can bring substance to where it's needed automatically. That's a big process that is called self-healing materials. It's been pretty much examined over the past 4 or 5 years, and there are quite a few examples of that. You can have elastomeric reinforced polymers. You can have, obviously a classic case is phase transformed toughened ceramics. So in fact you're healing a crack when it starts to propagate. And there's another fine trick. It's of polymers which contain encapsulated repolymerizing compounds. So when a crack happens, it breaks the capsule, which releases a polymerizing agent to close the crack. Pretty smart, but it works very well in materials that are already pretty much a disaster anyway. So, in fact, you're repairing a material as it is damaging. You can feel that it's not as good as bone, of course, because once you've released the repolymerizing agent, if a second crack appears, too late. It can only happen, it's a one-shot gun. Then you have self-repairing high-temperature coatings and so on. So here's the repolymerizing capsule. It's an iconic paper about these self-healing materials. You see over this little capsule, and basically the crack propagates and self-repairs. What I really wanted to show you were the classic ingredients of self-healing materials. If you look at these self-healing materials, oops, sorry, wrong slide. There must be obviously things moving in order for a material to heal itself. They need to move, and they need to move together at the same time as the damage is occurring. And to sense that that is going to work, there needs to be a fit between the damage timescales and the healing timescales. And that, in a sense, is going to create a kind of grid of what can reasonably be your wish list or your letter to Father Christmas, as it were. And then, of course, you need to have a capacity to feel the damage in order to sense the damage in order to repair it. So there are two broad families of self-healing materials. There's the ideal ones, where it repairs the damage at 100%, where it could repair itself an infinite number of times, where the repair is autonomous. You don't even need to sort of tap the material's shoulder and say, hey, come on, man, self-repair. Then, of course, the repaired material has better properties than the material it replaces, and it's cheap. That's what I would call the letter to Father Christmas. On the other side, you have the reality of things. Usually, you never completely repair the damage. You avoid huge damage, like sort of the material snapping. Usually, it only works once. Very often, it needs external stimulus, resulting in damage, and it has poorer properties than the material it replaces, and it's usually more expensive. So, a pretty depressing picture, but it's very interesting nonetheless, as long as you have a chart allowing you to evaluate whether you have chances of it working or not. This is one example of what this could look like. Hang on a minute, bear with me. You're going to look at the various types of damage and the various types of healing. So, imagine the function. If the function, for instance, is to bear a load, the degradation, deterioration properties will be a dissolution of precipitates, a coalescence. If you have protection from corrosion, it's the permeability to fluids that's going to be important. If you look at protect from wear, it's going to be hardness and wear resistance. Thermal protection, it's going to be thermal diffusivity. If you look at the type of decay that can happen, it's going to be, for instance, cracks, cavities, a destruction of the coating. And what we're going to need to look at is the type of healing that you can imagine. If you have dissolution of precipitate dissolution, you think the healing is reprecipitation. If you have an interface rupture, you need to reform the. You can have crack closure. as I was showing the propagation of crack in PMMA. You can have things that are as simple as saying that if you have an acute crack, if you can find a way of rounding the bottom of the crack, maybe you can prevent degradation, deterioration. So you have the variety of materials, the variety of damage, and the variety of healing methods. What I really just wanted to show was how can you have a simple scale to read all of that. You have a parameter that you're going to call damage. This parameter is linked to the stress subjected, suffered by the material, worsened by the fact that it's already damaged. And here you have the classic, you have the sort of Katchenhoff equation of damage. And then what you're saying is actually healing with a characteristic time that depends on the mechanism. Is it a diffusion mechanism, precipitation mechanism, or so on and so forth? And you can see that the characteristic time is going to vary. So I'm not here trying to have an exact description of the damage, but just the parameters that are going to allow us to say we have a chance, or we don't, to have something self-healing. And that's actually not too difficult, because you have an accumulation of damage which is called accelerates until the damage reaches the value of 1, and then healing. So when you do that, you have something that appears very naturally. That is the rate of damage that can be created, induced in the material over the characteristic time of healing. So you can see if that is very high, it's going to be tough to have a healing mechanism. If it's low, you probably will be able to have a self-healing mechanism. So that said, you've seen the essential. You have 3 types of behavior. You have one where if the rate of damage, and if you have a parameter k, where you have a lot of damage and not a lot of healing, the damage accumulates, and you know how things, you know that it's going to reach a nasty end. But you have 2 other situations where, depending on how the rate of damage can be connected to the sensitivity to damage, either you have a situation which is very nice here on the right-hand side, where you have a damage that is actually decreasing as damage occurs, and it reaches a stationary point. If you start with this state of damage here, it accumulates, and then it stays stuck here. So you have actually a system that's going to damage itself, and then things are going to calm down. Here, the system is going to damage itself more slowly, and then it's going to start again. And here you have really a slowing down as well as a self-healing. But what I'm basically showing is that it's very simple, with parameters which are sensitivity to stress and the damage rate, and a parameter here that takes into account both the rate of damage and the characteristic healing time. And you have simple rules to tell you whether or not there is a chance of obtaining a self-healing mechanism that can be efficient. So let's just look at the detail. You have the damage rate here. If you start from here, you reach point 1, meaning that things are not looking good. Essentially what it says is you have a critical damage zone here, where you're always going to have controlled damage, and then an amount of where you get more damage, whatever the self-healing principle is finished. You'll never make it. So I'll skip the algebra and reach the conclusions on time. What I have tried to show you with these 2 cases, that of creep and that of wear, is basically the rules to allow you to find that whether you can extrapolate rather than just interpolate. And the rules that have emerged are rules of identifying fields of dominance, regions of dominance between different mechanisms, and within those, to start with physically based models, microscopic. For creep, microscopic means interaction, dislocation of microstructures, where for wear it's the dynamics and thermics of asperities that are in contact. You need to use those to obtain models, which can be extrapolated, while remaining in a class where the dominant mechanism remains. And then an answer to that, a kind of reaction to these problems of durability, how you can mitigate the damage or even have a mechanism that tries to reverse that by healing it. What I wanted to show you was how you could have a vision of the various approaches to see whether or not it was worth moving in that direction. So thanks very much for your attention, and I shall now yield the floor to Eric Andrieux, who will tell us about corrosion. Just for those of you who were not there last week or the other weeks, this afternoon for the workshop, it is just as open as this morning. In the morning you have the lecture and the seminar, and in the afternoon the workshop, which is in room 4 at the entrance of the collège upstairs.